It's my great pleasure to introduce our speaker, Professor Xavier Prochaska, who is a distinguished professor at the University of California, Santa Cruz. And he is also an associated member at the Kavli IPMU at the University of Tokyo and the National Observatory of Japan. Professor Prochaska received his PhD in 1998 at the UC San Diego, and after that, he joined the Carnegie Observatory as a Carnegie and Hubble Fellow. And after that, he joined the faculty member at the University of UC Santa Cruz in 2002. Professor Prochaska is a world leader and expert on galaxy evolution. He has been working on probing the distribution of baryons in various forms, ionized, diffuse molecules in and out of galaxies across cosmic time, by utilizing the collecting power of large telescopes, including Hubble Space Telescope, CAC telescope, and ALMA in radio, as well as utilizing the statistical power provided by large surveys, including the Sloan Digital Sky Survey and the Dark Energy Spectroscopy Instrument Survey. And he is one of the pioneers starting to apply machine learning algorithms and techniques to the astronomical data sets. And a few years ago, he established a team called F4, Fast and Fortunate. I thought it's furious, but it's fortunate. Okay, Fast and Fortunate for FRB follow-up program to investigate the nature of fast radio bursts and search for the host galaxies. And with his data collected with his collaborations, he resolved a problem called missing baryon problem in galaxy and cosmology field. In addition to astrophysics, he is also working on physical oceanography, and he is a member of the Ocean Science Department at UC Santa Cruz. During his career, he has won many grants and awards from different agencies. Just named the recent two in 2020, he received the Newcomb Cleveland Prize of the American Association for the Advancement of Science for his contribution of fast radio burst study. And in 2023, this year, he received the Pivot Fellowship from the Simons Foundation supporting his exploration on the oceanography. And today, he's going to tell us about his research on probing the cosmic web with fast radio bursts. Without further ado, let's welcome Professor Prochaska.
I'm humbled by that, Tingwen. Thank you. Great to see you again. Tingwen was a postdoctoral fellow during the pandemic in Santa Cruz. I saw him some, but I think he didn't get the full Santa Cruz experience, but it's nice to see him here. Hello. My first trip to Taiwan. I'm enjoying it thoroughly. Thank you all. Those of you that have taken me to new places and lunch today and whatever else. I'm going to talk about fast radio bursts today, although I put in a slide for Paul Ho. Is Paul Ho in the audience? I don't think I've met Paul Ho. Taken he's not. So I think, as I recall, and I was going to confirm from him, Paul, myself, and Artie Wolf had a project together with the SMA about 15 years ago to study what I now refer to as the Wolf disk. Galaxies associated with damp Lyman alpha systems, in this case. Art Wolf on the right was my PhD advisor, the Wolf in the Wolf disk. And Paul, Art, and I were trying to measure these galaxies with C+ before ALMA. I am aware many of the folks in this building are ALMA lovers, so this is your ALMA for the day. Enjoy it. It's outstanding what it can do, and if galaxy formation interests you, check out this paper by another one of Art's graduate students, Marcel Neeleman. But I'm going to talk that part. And let's jump right in. First, the team. So F to the 4 is a collaboration of about 15 scientists, a handful of senior folks like myself, including Regina Jorgensen, Nicholas Tejos, Mike Fong, but most of the effort and excitement comes from our younger members, at UC Santa Cruz, at Northwestern University in Chile, at the Mariah Mitchell Observatory. Quiz afterwards if you can tell me where that is. Mariah Mitchell Observatory. And they're doing great work. So I'm here to represent on their behalf I don't think I'm presenting anything that I've published. I certainly have lead author in the slide that follow. And I should also give credit where credit's due. I do not detect fast radio bursts as a human being, or F4 does not detect fast radio bursts. We rely on folks across the world and who do it very well. And three of the folks that we partner the closest with, I would say, are listed here. And you'll see results, especially from the upper left, craft experiment on the ASKAP telescope in Australia. We've newly partnered with CHIME, and Meertrap is still up and chugging. All right, I believe you saw this gentleman last week, at least those of you that were here last week, Duncan, who kicked off this field by discovering serendipitously this fast radio burst. I was told you're all somewhat familiar with FRBs, so I will go through the introduction somewhat quickly. My apologies if you're not so experienced, but let's see what we can do. When I give this talk to this is a general audience, but whatever, astronomers that don't work on fast radio bursts, I say this is an image of an FRB. It's as pretty as it gets. No grand design spirals here, but nevertheless, this is beautiful. Beautiful signal. Arrival time, frequency, you've been taught by now that the arrival time of those photons is retarded because they're traveling through a plasma, and that speed is retarded according to the frequency squared. That leads to the dispersion of the photons, and we quantify it with the dispersion measure, dm, not dark matter. DM, I'm sure this DM existed first. I don't know how the cosmologists took over DM for dark matter. But anyways, dispersion measure, which is here given in integral form, the integral of the electron density between us and the source, weighted by the scale factor if you go to cosmological distances. So 1 plus z in the denominator. I recall sitting on a couch in Santa Cruz discussing this paper over coffee. We had a morning coffee, and thinking, whoa, this could be useful, because it was certainly, and it certainly is, the ultimate way to count electrons. That was 2007. 2007. Duncan, I'm sure, hopefully described better than I could possibly, so I won't even try, how this data sat on a hard drive for 6 years, and then was somewhat serendipitously discovered and led to FRBs. I got excited by FRBs, that paper, because of this guy, who I saw last week in Tokyo. This is Masataka Fukugita-san, who published this paper. If you can't read in the back, that says the cosmic baryon budget. Ooh, that's a cosmic baryon budget. It's published in 1998 when I was just graduating, as we heard, PhD. And Masataka and his co-authors counted up, did a census of baryons in the current day universe, modern day. Counted up the stars and the gas, atomic and molecular, and the ionized gas and clusters, stuff we can see with our telescopes. So it was an empirical estimate. And I don't think he made this pie chart, someone else must have along the way, but the pieces that we could see with our eyes, with our telescopes, were the small wedges here, stars, cluster gas in the black. And they pointed out that the total was much less than what we know is there, strong word, from cosmological early universe measurements of deuterium, something I've worked on, and the CMB. Two different experiments, same answer. That's one number I would go to my grave with, how much baryons in the universe. And yet, embarrassingly, in our backyard, we can't find that material, at least not in 1998. This beget the missing baryons problem that plagued me for a few decades. I used every telescope that Tingman just mentioned to attack the problem. The Keck telescopes, the Hubble Space Telescope, Chandra. I didn't use so much Chandra. Other people, X-ray telescope. Oh, Chandra, pointed the wrong one. And this telescope. Anyone? Here's quiz time. What's that telescope? we have 50 astronomers in the room. This is probably a $200 million taxpayer investment. What's that telescope? New Star is not correct. I like that guess.
That's long.
It's long. That's right. To focus X-rays. This is an ultraviolet telescope. There's only 3, so that I can count. Rosat's X-ray. Yeah. Swift is not a bad guess. It's still not. Yes, it has UV capability. I would not call it UV telescope. Still not
UV.
UV, ultraviolet.
EUV.
EUV is one of the 3 you should be able to guess, and that's not it. That's not HST.
And it's not IU.
Correct. Someone just said it. Fuse. Were you on Google or did you come up with that yourself? That's the Fuse satellite, which was far ultraviolet, which is a niche community, but very good for finding diffuse plasma. But it too failed, in my opinion, to detect missing grounds. Enter fast radio bursts. Maybe you've heard the story by now. I'm only going to go through quickly today. Cosmic web from a computer. We don't take images like this with our telescopes, unfortunately. We cannot. We do have galaxy surveys which have that type of structure, so we believe in it and have evidence for it. But this is a computer simulation. The arrows are pointing at where we call galactic halos reside, so the dense regions of the universe. The other arrows, the intergalactic medium, the gas between galaxies. Those arrows are pointing between the galaxies and are the diffuse matter that lie in between and make up the majority of the mass in our universe. So the target with fast radio bursts became this equation. I'm going to refer to it as DM cosmic for the cosmic web. The angle brackets there mean average. So the average cosmic contribution to the dispersion measure of a source, like a fast radio burst, is this equation. And it's first principles, cosmology. This stuff is the DS that you saw in the definition of dispersion measure, except for one with Z's. There's another one there. But the main target here is the NE, the electron density. And for in this neutral universe that we live in, for every electron, we have a baryon, proton. So that's how we count electrons by measuring the cosmic dispersion. So we set out to do this. 2007, it became a light bulb went off for me, but the technology was not there to do this measurement. The game changer of the last handful of years was this facility, ASKAP, radio telescope in Australia that not only detects FRBs, but because it's an interferometer, localizes them to arcsecond precision and better in one go. Keith Bannister, the PI of the team known as CRAFT, and was the lead author of the paper that won that Cleveland Newcomb Award, something like that. Our main contribution has been taking those localizations and doing, it's kind of easy work, finding the galaxies, taking a redshift. Within the signal of the FRB itself, there are a number of things one can derive, including the dispersion measure, but nothing that is especially precise in terms of the redshift. So when you hear about the redshift of an FRB, typically, maybe always, that means it's been localized to a galaxy and the galaxy's redshift has been measured. It's a probabilistic game. I'm happy to discuss that at length if you wish. That is, you never know for sure the FRB came from that galaxy. But you can make an assessment of how probable that association is. Our team uses a Bayesian approach that we actually introduced, and then getting the redshifts, by and large, not so challenging with a big telescope. So, measure the dispersion measure, that's very precise from the FRB signal itself. Measure the redshift from the galaxy that you associate with, you're done. Then you can test cosmology. This is that dm cosmic, the black line, as a function of redshift. So that equation evaluated with omega baryon that we derived from CM. That's coming through the audio. I hope they're not disagreeing with me. That's the M cosmic from the equation you saw a few slides back. Function of redshift. The band is a guess, a model of the physical scatter about the mean. I'm going to talk more about that as I go. But it's a model. We don't. I'd say the black line we know, to the precision that we know the numbers in that equation. The gray band we know less about. And formally, dm cosmic is the signal we observe or measure, the number we measure from the FRB minus an estimate for the gas in the Milky Way. I think Whaley and I still disagree about one of those numbers, probably a factor of 5, but it's in units around here, tens of dm, that was our disagreement, not hundreds. And then the amount of electrons in the host galaxy, which is an unknown, is a nuisance factor. And it goes into the modeling that comes more later in the talk than right now. Anywho, J.P. McCord led the paper from ASKAP and Kraft on testing the little baryons in the nearby universe. The colored dots are the part of the sample that met strict criteria. The party analysis, they fall along the line, led us to publish the McCord relation. It's now named after JP, who passed about a week after the publication. Untimely passing. I gave the talk in front of Masa talk about 6 months later. He felt that yes, he could stop. We could stop worrying about the missing baryons problem. So that was good enough for me. But we've detected the baryons, say with that publication, and subsequent ones. We haven't figured out quite where they are. And that is where a lot of my interest lies with fast Fourier bursts today. This is a pretty, maybe too complicated diagram for one slide from a recent work by Ilya Kirkin, showing a prediction for the universe, numerical cosmological simulation, galaxy formation, all the bells and whistles. Simba, if you know your simulations. So feedback in its various forms in the top 2 panels, a no feedback scenario of the universe in the bottom 2 panels, and you're supposed to be impressed that the fraction of baryons, that's what's kind of color-coded here, differs rather significantly between the 2 models of the universe. One with a substantial amount of feedback, one without. And so from first principles, we cannot predict where the gas resides.
But this has a lot in stars, so that isn't that a measured number, what omega x stars over omega baryons?
Yeah, well, it's measured to a factor of 2. This model's probably ruled. This model is ruled out.
Okay.
Sorry, I should even say it that strong. I should say it that strongly.
Okay.
But there's everything in between.
Okay, fair. Yeah.
Yeah. In fact, I'll show you one I prefer on another slide in a moment. Okay, that's motivation. Here's today's outline. I got through the introduction. We may get through all 3 of these pieces, we may not. And that's fine if we don't. But let's start with capital F. And what we are measuring and then leveraging is this back to the dispersion measure of the cosmic web. There's structure in the cosmic web. Nobody quibbles about that. As a result, if you have an FRB along one sightline versus an FRB along some other sightline, this sightline, which happened to intersect even perhaps a cluster of galaxies, okay, has seen more matter than this sightline, which I've drawn to avoid pretty much all the galaxies. So there was the average quantity. If I run an infinite number of red arrows through the box, I have to get that average. But you'll appreciate there's going to be can be substantial scatter about that average physically. It's expected. And then the more, to the extent that galaxies do blow their gas out of themselves to large distances, the more homogeneous the distribution will be. So there'll be less scatter about the average, the mean. The more baryons collapse into structure, the bigger the scatter. And then you have almost Poisson fluctuations. That's it in words. Those of you that work on galaxies probably say the word feedback once a day, maybe 10 times a day. It's a recipe, part of the prescription of how a galaxy forms, has been for a long time now. There's evidence for it as well, not just required, say, for theory. There's evidence in the data. This is a colleague of mine, or former colleague of mine, Ben Wiener's paper showing magnesium O2 emission, so nebular emission lines from galaxies. It's an ensemble of galaxies, probably, I can't remember, 1,000, 10,000 galaxies. And then absorption from those same galaxies in magnesium, one of these T1's most expert on. And you can see that absorption is blue shifted. It's shifted to the left, suggestive, or maybe even indicative of a flow of gas towards us, aka an outflow. Galaxies do shove gas around, some of it towards us, or away from it, more important. How you put that into a computer model, you can get rather wildly different predictions for how much material stays within the dark matter halo. So that's what's plotted here. This is the mass of the dark matter halo, 10 to 11, 12, 13. This is massive, very massive, almost cluster mass. Two different popular computer simulations, FIRE and TNG, very different results, or quite different, order two different results in how much matter is retained within the halo. They have that freedom to do this because there are not excellent constraints on gas on these scales, ionized scales. Ionized gas on these scales, where most of the mass lies.
Why does TNG go up and down?
Ha! Why does TNG? Sufficient feedback, I'm going to guess, I don't know this for sure. Sufficient feedback to blow material out of the galaxies, probably AGN even turning on, actually I'm not sure which TNG model that was, that's a real guess. And then eventually the dark matter halo becomes massive enough nothing escapes it. So I'm sure their clusters are bound. Yeah. This part I get, yeah. What peculiarity, I don't know. Okay, so I've shown you this. Now what we're after is the scatter in this relation, and I'm going to parameterize it as follows. Matt McQuinn came up with this description of the scatter in DM cosmic. And sigma is a parameter of the model, and f is a parameter of sigma, and f is what I'm after. This is the full PDF. I'm not going to go into it in depth unless you really want to know, but f is a parameterization of the scatter in DM cosmic. We expect something like this redshift dependence because the more distant the FRB, the more structure it goes through, you beat down some of that Poisson fluctuation. So the biggest, intrinsically the biggest scatter should be at the lowest ratios. Good on that? Okay, so I've been discussing DM cosmic. That's what scientifically I'm focused on. However, as I kind of almost glossed over, we do not have a direct measurement of the host contribution to the FRB dispersion measure. And so that has to be part of the model too. And so the observable really becomes DMEG extragalactic. You will, at least for now, allow me that we can estimate the Milky Way contribution and ignore it or subtract it. So we model DMEG. How do we do that? I give full credit to Clancy James, who's in Australia, who, for our team at least, has put together the model. It's involved. There's 8 free parameters these days in the model, and assumptions as well. 2 parameters for the host dispersion measure distribution. We use a log normal PDF. A few for the energetics of the FRB, a few for the width of the FRB, numbers for the telescope that we're using here, ASKAP. We allow Hubble's constant to vary, and in part because we wish to constrain it. And then this F that I've introduced to you. And so what's plotted, this is redshift, this is DM extragalactic, red are data. Red dots are data. And underneath is a model that was constructed by varying those pieces. It's a Ford model. And F is what the results I'm presenting today are F, which were actually done by this gentleman, Jay Baptista, who's now a graduate student at Stanford. To give you a sense of what F does to that PDF, here's an illustration. On the left is a very low value of F. So no scatter, or very little scatter about the average. That's what you see. Very little scatter towards the mean in correlation. And a very large F, large scatter about the mean. Intuitively, that's how the model changes if you change F. If you want a greater depth, most of the actual statistical power from the data lies on this side of the distribution, which you can tell even from the drawing is very steep. The point being, if you observe an FRB here, or the laser pointing, which I always say, clearly that model is ruled out. But I can detect them up here, and they're not, that's disfavored, but not killed to the extent that a single FRB can really rule out strongly a scenario like the one on the left. So this right-hand side is where the action really lies. Here's J. Here's his constraint on F from 16 FRBs with redshifts and some order 50 additional ones without redshifts. Today, we have a one-sided constraint, aka a lower limit, on F. That's what's plotted. There's a lot of curves here. They're making different assumptions for H0. You're probably aware there's controversy in the community over what. We're back to arguing over H0 again. I guess when I started doing astronomy, we were arguing over H0. Then we stopped, and now we're repeating ourselves. But now the question is it 67 and 73, not 50 and 100? Maybe that's progress, but we're still debating. Anywho, there's our constraint on F.
Why does F stop at 0, log F?
Only because we already consider this to be unphysical. You could let it be higher. I think my prior would be there's no way the universe has such a high F. So call it a prior. But we have no constraint. It could be it could be as high as you want. It's a lower limit today. As plotted here, a lower limit on F. Oh no, I didn't put the F values. Well, that is the same value as here. Probably the 99th percentile, maybe the 95th percentile. So in log F, it's minus 0.75, and in linear, it's something like 0.3, 0.25. Data, the black, and then 3 models of galaxy formation with, in this case, they're varying how much AGN contribute to blowing up galaxies. And you can see the Symbol model is already starting to have some problems for most of the parameter space. So even with only 16 FRBs, we're starting to rule out Symbol's a pretty, I don't want to say vanilla flavor, but a common model for galaxy formation.
Basically, how much does this depend on assumption on how to construct?
You get a sense of that from this figure. So a lot, or enough. Let's see, H now, the dashed line. So just compare the dashed line with the dashed dot.
Yes, that's a systematic difference depending on assumption.
Yeah.
H no.
Yeah. I doubt H is beyond. I doubt H is outside these boundaries. So.
So this vertical dashed line is shown in the horizontal line in the next year.
The vertical dashed line is actually a previous work on theory, which was an okay agreement with the data. Sorry, I should do that.
Sorry, could you tell me the relation between the next of the
So I have a lower limit on F. I don't know.
Okay,
95%.
Okay, that's
That has to be bigger. In the next slide, we point that.
Oh, okay. In that sense, it doesn't depend on how constant here because it's rolling.
Well, there's still an assumed value, but I don't know if these authors took the most conservative or there's some depend.
Oh.
Other questions on F? It's going to end part one shortly. Here's where we think we'll get to, perhaps with 100 FRBs, with a precisely measure H naught. This is a forecast if H naught eventually, gravitational waves will get H naught. I'm not worried about that. This is the kind of constraint you get. The 100 FRBs with redshifts. Just a forecast. So that's one of the areas I'm headed towards, I hope. And others will, I imagine, do this.
The lower bound, doesn't that assuming that there's zero scatter in the host DM? In other words, couldn't you always allow a log f of minus infinity if you say all the scatter came from the host?
No. The host only adds DM, Whaley.
That's assuming all your gas is in the IGM.
It's assuming all the gas is in the IGM.
Or that there is a lot of gas in the IGM.
DM extragalactic is IGM, is cosmic, I use, I'm precise in my language, is cosmic web plus host. They're both additive, right? And so I can make DM host much bigger, of course.
That's assuming that, I mean, not that I subscribe to this, but purely logically, if you said that some crazy people say that all the baryons are in comets, and there is no IGM, in which case all the DM you're observing is from the host, for example, as an extreme limit, in which case couldn't this shift arbitrarily?
Yeah, I'm not going to entertain that crazy idea. They're not. All the matter in the universe is not in comets, so I hate to disappoint you.
Guys,
But the point about the DM host is an important one.
Yeah.
It only is additive, so that's what I'm saying. As soon as you detect an FRB here, that model's killed.
Mm-hmm.
I don't care what you want to think about the host.
That's you cannot have negative DMs.
Correct.
Right, you can only get there by scatter in the IGM itself, sure.
Correct.
I'm assuming that the redshifts for the FRBs are not known or not precise.
Did you just come in? Yes or no?
I did.
Okay. Sorry, then I went through too quickly with this. Go ahead, ask your question.
So the redshifts for the FRBs, are they first determined in all the sample with lines, let's say, absorption lines?
Absolutely. Every one of those 16, this process was done, and every one of the 16 had a posterior probability of association above, I can't remember off the top of my head. I'm going to say 90%, but you have to go look at the paper. And the one that's close to 90% has a neighbor next door, taking up some of that posterior.
Which is same redshift anyway.
One of
Similar.
them, yes, and then there's one that I've published that where no, it's foreground.
Mm-hmm.
Maybe there's two close to 90.
Just quickly, how do you correct for the observational bias? So if DM is large, then there's more scatter, and it tends to.
That's a great question. We do not. Well, sorry, that is baked in. No, I should not be so flippant. Great question. So the question was. Let me rephrase it. The gas in between us and the FRB can scatter the signal, broaden it, make it more difficult to detect with the telescope, and then not be detected with the telescope, aka a bias. That's in this model. And that's partly why this PDF looks the way it does. I've had to stare at this for hours and hours to fully digest it, so you're not going to get there. Well, maybe you will. I assume you're not. Notice as DM gets higher and higher, the PDF goes to the left. That should make your head hurt. Right? The correlation says that as DM gets higher and higher, I should be going this way. But the PDF says otherwise. And that's because we do have a finite telescope. And that's, what's it called? Smearing, dispersion smearing? What do we call it? that spreads out the signal.
Scatterpot, no.
No, not dispersion scattering, just
dispersion scattering.
dispersion scattering. So that's also a key, an important effect here. Another bias is you cannot detect with this telescope, we don't believe, a very high dispersion measure at a very high redshift. So yes, you do have to consider it. I doubt we have it right. So back to your question, yes, you concerned about that. We are, but here's an attempt. And undoubtedly wrong. This model will definitely evolve. But great question. Yes. All right. All right. I'm going to skip part 2, largely. And the main reason is because KG Lee's going to visit you soon. Do you know when?
2 weeks.
2 weeks. Come on back. And have some new results on this, better than I was going to show today. And he's leading the project, so come back for that. I'll set the stage, maybe, do not much more. We've been talking about these two. Let me emphasize, physically, DM cosmic, there's nothing profound here, will correlate with cosmic structure. DM host, probably, we haven't shown this yet today, will correlate with something to do with the host galaxy. Yeah. And so to the extent that we can cross-correlate the FRBs with these things, we can have some hope of distinction. He will talk, KG will talk more about, probably only about this. We're working on this, but there's no obvious signal yet that I've seen. The student involved is Sunil Simha. He's a graduate student on the market. I told him to apply to your job. He's kind of paved the way of correlating or describing the foreground structure. I'm going through the slides quickly. Of FRBs. Here he's getting rid of stars, ignoring stars, and then foreground galaxies and their dispersion measures. I'm skipping a little bit, sorry. Come to KG stuff. Instead, I'll kind of finish today with the Redshift 1 universe, which is the frontier. Posted to archive a year ago, published in Science a couple weeks ago. That's how long it takes to go through Kevin Smith's desk, the editor at Science. He's great, but he's slow. Anywho, FRB detected with ASKAP. There it is. I don't think there's anything too special about it. I mean, they're all snowflakes, but this one's kind of run of the mill. Observe the localizations, the black circle. Galaxies, or galaxy close. So far, no redshift, G-band, R-band, very large telescope. And then spectrum of the various clumps in that previous slide. Revealing a redshift of 1. This is the O2 doublet. So the redshift is unambiguous. Excuse me. And for those of you who've been on the field, the record holder, in my opinion, was redshift 0.5. Maybe it was 0.6, I can't remember. And so we just leap from 0.5 to 1 in one go. It's kind of cool. This is not published yet, but will appear in archive next week. Alexa Gordon's leading it. These are HST images of the same galaxy. Now even I start to hedge. This is a complex system apparently. This is unusual for galaxies at redshift. Certainly today, even at redshift 1, this is a bit peculiar. Call it a group if you like. That word means a lot of things in astronomy, but anywho, there it is.
So those two images are the same?
Ultraviolet, observed ultraviolet, so restrant ultraviolet for sure. forget what wavelength, probably 2008.
Yeah. 606, so 6,000 things. But rest frame would be.
Thank you. Sorry.
Yeah.
Optical. Not UV. Rest frame, yeah, approaching alt UV. And then near infrared. 1.6. Ooh, so nice data. Alexa's leading the paper. As far as hosts go, it falls in the locus of star-forming galaxies. The gray is cosmos, field galaxies at redshift 1. So nothing too peculiar there.
So I assume many galaxies over there. So which galaxy are you showing?
I don't remember. That's a good question.
It looks the same.
I don't remember. This one is, despite what it looks like, this one's a lot brighter than the rest. It's probably just this one. I'm pretty sure. But even if it's not, the light's dominated by it. Good question. This is a locus of redshift versus some metric of the how long the galaxy's been forming stars for. And again, the gray is cosmos. This galaxy. At redshift 1, this one doesn't stick out in that description either. I'd hoped nobody could make a slide for me that says, hey, discovering this FRB at redshift 1 means we can discover many FRBs at redshift 2 or 3. So use your imagination. But that FRB was bright. It was easily detected by ASKAP. And it's at redshift 1. So redshift 2 is definitely going to happen. If you're worried about FRBs, that would the community? Yes, they will. Which is another, perhaps in my view, the most important part of that result. Great. All right. Now just a few slides to wrap up. So what's next? I made this the other day. This is kind of cool. The field is quickly becoming data rich, right? So many of us maybe got excited in 2007. In 2017, we localized a 2012 repeating of FRB. So that's the first. These are ordered by FRB TNS. And now the community has done, what is that, 60? The order of 50 or 60 arc-second localized FRBs. And CHIME has dominated just the total number of FRBs. And this is now a few months out of date, so I'm sure they've gone past, I think, no, they have not gone past 5,000 yet. Certainly by 4,000. So, what am I going to do with all that? Because everything I showed you today was on 20 FRBs, 30. And there's more. So I got to visit, I used to keep calling it Burst. It's Burst. Blast? I'm so sorry, I can't remember names. Burst. I got to visit the Burst site yesterday, where the PI himself was tinkering. I guess this is how you reduce costs. You send a director. I'm no good with a screwdriver. Things weren't going so well. There were some issues yesterday. There always are with projects. But I'm no expert, but this could be the problem. I don't know. Consider it. It was pecking away at some little wire there. All right, so the technology is not slowing down in this field. As much as, this is cool. Another order of magnitude is for sure on the way. And Whaley tells me he won't sleep until there's 1 million FRBs discovered a year. That's way off the plot. Burst, one of its great attributes will be to find nearby FRBs. That allows you to search for the event in other wavelengths. We're trying today with what we have. This is a publication you'll see tomorrow, I think. Trying Kilpatrick, we're using a high-speed camera on the 8-meter Gemini telescope. These are data. This is a non-detection. This is the FRB that goes off every 16 days, roughly. So we were able to point Gemini right as it's transiting CHIME and detect and observe it at the same time the FRB existed. Now, I'm not showing you the FRB, but trust me, there was an FRB pulse. 2 cameras, that's why there's 2.
What's the time resolution?
10 milliseconds. Which is pretty nice. And that lets us put a fluence upper limit optical to radio, shown here. Which probably doesn't excite too many theorists, to be honest. Gotta start somewhere. And do you remember? I don't remember the redshift of this. I think it's like point. Yeah, I don't remember. 0.03.
0.03.
Yeah.
Excuse me, does this mean the pulse of magnetosphere is already ruled out for this case?
I'll say yes. Read the paper tomorrow.
Oh, yes.
I'm sorry. That's what the plot says, and I should stick by the plot.
That's amazing.
I think that makes a lot of assumptions.
Probably.
That, I mean, if you take, for example, the crab, where's Sujin, who's our local expert on these. So if you take the the problem, of course, with things like the crab is that the very brightest radio pulses do not result in correspondingly bright optical flashes. So in other words, this is a mean ratio of what they do. But you're selecting for the very, very brightest, the optical that's empirically in crab doesn't go up. So the ratio is probably 6 orders of magnitude higher for the crab if you were to select on only the brightest event.
That said, for this FRB, it's nowhere near the brightest. I appreciate it's still bright compared to pulsars, but it's nowhere near the brightest for this FRB. Anyway, this works, yeah, in its nascent state, but I think terms like burst will enable it here, there, and everywhere, which is great. F4 has partnered with CHIME because of this, the Outriggers that they're building and now commissioning. I'm not at all involved in that work. There are 3 of the students. There are more folks involved in that effort, and it's working well. This is a localization from just the KKO Outrigger in CHIME, which gets you about a few arc seconds this way and about 15 that way. Which, when I heard that the first time, I was like, oh, that's actually kind of useful. How useful? Well, I am very confident in that association. I am very confident in that association. I think CHIME will pass up all the other experiments, even with just KKO, by the middle of next year, with associations, not just localizations, but associations. So that's cool. That's it. I'm done. Here are a number of things that excite me with FRBs. I haven't updated this recently. Hopefully it still holds what I think is going to happen. I'll go through them. We're going to place constraints, we already are, with scattering on ISM turbulence and galaxies. We're going to learn about how gases distribute around galaxies, what we call the CGM. We may get H0 to 10%. Not so exciting, perhaps. We're going to nail M31. That's going to be so cool. We're already placing constraints. We, the community, not involved in many of them. We're going to already place great constraints to black halo. I think we'll observe the WIM. Ask me what that is if you want to know. It's not discussed much these days. Whaley was at the heart of Princeton when the WIM was invented. Maybe you were involved in it.
Warm, hot, intercluster.
I always think it's ionized or intergalactic. I think it's just ionized, right? Warm, hot, ionized medium.
Ionized medium.
There's a lot of optimism to do lensing with FRBs. Maybe learn more about the last phase transition of the universe, aka human reionization. I don't know. And that magnetic fields, well, IGM magnetic field, that's hard. And that. Thank you. Thanks for your time.
Thank you, X. Any questions? questions for Professor Prochaska?
Okay. Thank you very much for very nice talks. I saw so many new things here. And I have one question about the high redshift FRBs. I'm really interested in this. And then initially I saw high sensitivity radio telescope might have more chance to do the high Z.
They should. They must.
They will. But as far as I know, the first in China, so they don't. I don't think they detect very high Z FRBs.
Well, they have very high DMs.
High DM, right? So
That's
that DM is probably not as high as what CHIME detect. For example, CHIME is up to 3,000 or so, right? Then
I don't know enough about FAST to say otherwise, but
Oh.
I would agree with you. I would expect them to have the highest DMs.
yeah, and if I look at the ASKAP's result, then already detect the resolution 1, right? So then I was wondering which would be better way to detect the high FRB. Say ASKAP has wide field of view with lower sensitivity compared to past. So therefore, wide field of view is better to detect bright event, high Z.
I haven't seen a calculation, but my gut tells me this is going to be the high Z confirmed because you need the association generator. FAST doesn't localize,
Right.
so you'll never is a strong word. You'll never know the redshift. To the extent that we associate with a galaxy, you need interferometer, and CHIME is. I'm aware. Let's see. It's even in this plot. Some of these are unpublished mirror trap FRBs with high DMs that we're trying to get the redshift for. So you may know about more beyond redshift 1 before. Mirror traps. Mirror cat is more sensitive than ASKAP and more sensitive than CHIME. Is that right? Probably. So I think.
Yes. Trap localized.
Oh yeah.
Oh.
It's an interferometer.
Oh.
Yes.
So I have a related question about this redshift 1 FRB. Can you estimate the number density of the FRB at that high redshift?
Only in the model, which has not been reevaluated for that FRB properly yet. So the answer is not yet. Today has that been modeled, but yes, it can be.
But you have a survey area. And
Yeah, absolutely. So in this model, which is published, you can work. All those numbers are here. And while this is the redshift 1 FRB, this was kind of the dot's been thrown there. It exists, but it's not part of this model. So it's not informative. Maybe it has. Yeah, I think it has. Send me an email. We can send you this updated model. For what it's worth. It's going to be pretty nice, very nice version. Please.
About the ratio between optical and radio emission from the magnetosphere. The key parameter is magnetic field strength and relaxing. For really young particles like clouds and mini clouds, they are emitted from the outer magnetosphere. However, for most cases, the radio emission are emitted from the polar regions or slightly above. However, optical emissions are not emitted from the outer magnetosphere. Therefore, to determine the ratio, the key parameter is the magnetic field strength for the relaxing for the magnetic moment of the neutron star and the rotation area. If the optical emission is stronger.
Okay, thanks. Any more questions? Please.
I'm also interested in that the optical simultaneous observation.
Yeah.
Could you tell us more about the strategy? So you said when CHIME is passing through a repeater, you're observing just the location with Xavier.
Yeah, so this FRB, it's R3, R6, doesn't matter.
Last week.
3, thank you, was previously demonstrated to repeat about every 16 days.
Okay.
That's
okay.
So
you know it's
easy. We took advantage of that, and then it doesn't always repeat. It doesn't always. It's not perfectly 16 days or whatever. So, but
what's the plan in the future? That you continue to monitor this one?
this one we have an ongoing program
Okay.
to observe.
So when
Because well, for what it's worth, the radio fluence was low here, although being told, I don't know how to interpret that, whether that's better or not. But anyways, R3 will continue to try.
okay.
Have you considered M81?
M81's FRB, is it quasi-periodic or anything?
Well, it's fairly busy. It's not periodic, but it's fairly busy. That's
Good point. No, we should. Maybe. Well, I forget what's in the latest proposal. I don't remember if we included it.
because that gives you by far the best limits in
close.
ergs because it's close, right? You get by far the best limits in total ergs.
Yeah. We should. Thank you.
So I just want to understand the argument about the DM cost. And if I correctly understand, so we don't know DM cost, so therefore there must be variation on the DM. And then when you estimate F parameter, so this is you are measuring the variation in DM
Right.
EG.
Yep.
And then does this variation in DM cost affect the F measurement?
Yes.
And then, in that sense, these two are degenerate, or
No.
how do you?
No.
No, you can separate these two effects.
They're not degenerate. Not strictly degenerate. That's right. So, this gentleman phrased it the best. DM cosmic will spread you about the mean in both directions. Right?
Is it?
DM host only pushes you in one direction.
now. So these two effects are basically different. So
They're different. They're not orthogonal.
I mean, in other words, if you found a DM of 3,000 FRB, you would not. It doesn't prove that there's a lot of IDM between you, and more likely than not, there is not. But if you saw a DM way below that, then it really tells you something because the
Yes,
DM
yes.
host cannot be negative.
cannot be negative. I see.
But so H naught matters, we've discussed that. Sigma 8 matters and is not known at perfect precision. What else am I worried about? What's the main two?
But that means so you also have independent estimate for dispersion in DM cost.
It's part of the model.
From
Yes, we get a
this
best
model.
estimate. For sure.
What would be the number?
It's so it's a orthogonal PDF. The mean I think is 180. I forget sigma. It wouldn't mean anything to you anyways. And median is 400. Median I think is 400.
Median to the host is 400.
No, it must be the
This is
other
a
way
orthogonal
around.
PDF.
I mean, that's good.
It's got a big tail.
So the median must be
Ah.
lower than the
No,
mean.
I misspoke.
Yes,
He's on it. The median is 180.
Yeah.
The mean is 100.
Oh, I see.
Sorry.
Oh,
Thank you.
oh.
The mean's definitely higher, but I forget. Sorry. We should check the paper. I can't remember the number.
Yeah, so it still makes it harder, but I mean, as you say, it's clear. The low one, you mentioned that this edge at the end that tells you where, so really gives you the information. It's nice.
Yeah, you got it. So the full PDF of the cosmic DM should probably also be asymmetric.
It is.
And you're parameterizing only with the first order-ish F.
Oh, this is asymmetric. I assure you, and highly. And it's a good description of most people's predictions from the cosmology simulations.
Okay. So I guess
I simplified it.
Right.
This is not simple. This is what we use.
Then my question would be shape deviation from your fiducial model that collapse everything into F. So I guess there must be information on the shape of the PDF of cosmic DM, but it might be difficult in reality because of other effects. The distribution of host DM, that kind of thing, is also asymmetric. And have you thought about, I guess,
Not yet. The dated 16 FRBs doesn't warrant it yet. Equan's pointing out that's not going to be sufficient. It won't be. 16 FRBs not. It's too early to bother. Maybe at 100. So yeah, this is, I'll rephrase it as well. This is overly optimistic because it doesn't allow for shape uncertainty.
Okay, any short questions? So Professor Prochaska will join the team after the colloquium. So if you want to talk to him, you can actually join later. So let's thank this talk.